Commercial aviation faces intense pressure to cut carbon emissions and slash fuel costs. Yet the entire global fleet relies on a propulsion machine whose basic physics have remained consistent for over half a century. To see how engineers are attempting to break through the current limits of flight, we must look at the original mechanics of the jet engine. Every gas turbine operates on the Brayton cycle. Huge volumes of air are pulled into the intake and squeezed into a high-pressure state. Fuel is then sprayed into this compressed air and ignited, blasting through a rear turbine and out the exhaust to generate thrust. Mastering those four physical steps, intake, compression, combustion, and exhaust, dictates exactly how far and how fast humans can travel across the globe. Most of the air rushing into the intake of a passenger jet never actually enters the central core to be burned. Instead, a massive fan at the front pushes air entirely around the outside of the core. This is the bypass ratio. Higher ratios result in engines that are quieter and significantly more fuel efficient. Engineers have spent decades building wider front fans to increase this ratio, but they have hit a physical limit. If the fan diameter grows any larger, the engine housing will scrape the tarmac during takeoff and landing. Because they cannot grow outward, the aerospace industry is trapped in a physical bottleneck that restricts future profitability and environmental goals. 3 corporate giants are currently competing to solve this efficiency bottleneck: General Electric, Pratt & Whitney, and Rolls-Royce. Rolls-Royce has historically focused on the wide-body market, utilizing their massive Trent engine family to power the largest twin-aisle jets in the world. Pratt & Whitney instead targeted high-volume single-aisle aircraft. They introduced geared turbofan technology, which uses a gearbox to let the fan and the inner turbine spin at different, optimized speeds to maximize efficiency on smaller planes. By specializing in either long-haul power or short-haul volume, these manufacturers divided global aviation into a high-stakes competitive landscape. The largest player in this market is CFM International, a joint venture between GE and the French firm Safran, which commands a 55% share of the industry. GE maintains its lead in the wide-body sector with the GE9X. It is the largest turbofan ever built, designed to produce record-breaking levels of long-haul thrust. Contrast that with the CFM LEAP series, which is engineered for the narrow-body market. It is designed to fit into the tight ground clearance constraints found under the wing of aircraft like the 737 MAX. The economics of these designs are absolute. Fuel accounts for up to 30% of an airline's total operating expenses. The manufacturer that increases bypass efficiency within these physical boundaries will capture billions in market share, securing dominance over the next generation of flight. Engineers are now attempting to bypass the size bottleneck by looking inward, developing compact cores through projects like NASA and GE's high-tech. By shrinking the internal combustion core, the bypass area inside the engine housing increases. This yields better fuel efficiency without expanding the engine's external dimensions. The industry is also moving toward hybrid electric architecture inside the gas turbine itself. Manufacturers are embedding electric motor generators to inject extra torque during takeoff and extract power during descent. This treatment of a jet engine as a hybrid system can reduce fuel burn by as much as 30%. Integrating electrical power into the thermodynamic cycle turns a traditional jet engine into a hybrid machine, directly reducing the reliance on jet fuel. The most radical approach to propulsion is the open fan architecture being developed by Airbus and CFM under the RISE program. This design removes the outer engine cowling entirely, exposing the fan blades to the open air. This allows for an unbelievable 50-to-1 bypass ratio by moving a massive volume of air at lower speeds. This redesign targets a 20% reduction in fuel consumption and CO2 emissions, while making the engines compatible with future sustainable aviation fuels. While the core physics of compression and combustion remain unchanged, the manufacturer that successfully masters compact cores, hybrid systems, and open fan architecture will dictate the sustainable future of human flight.